And with that, I'm going to pass this over to Pakita, who is the one of the co-chairs of the ETOS working group, and she will be presenting today.
Okay, thank you, Kristen. And thanks to Mike, too. I think this is a really great idea to have these webinars and try to reduce our travel and still be able to communicate with each other. So I'm representing the U.S. Eastern Tropical Ocean Synthesis Working Group. And we have been looking at this persistent problem in the couple climate models of the SST biases in the Eastern Tropical and Atlantic Pacific Oceans, and coming up with our assessment of what's known about them and trying to identify promising areas for future work. So to get us oriented, I thought I would show this figure that's been adapted from Toniazzo and Welmo from 2014. The upper plot shows the CMIP-5 model mean SST biases relative to the Hadley observational construction. And the thing that pops out on it are the large warm biases in the Eastern Tropical and Atlantic Oceans. In the bottom panel, you see the bias in the precipitation relative to CMAP. The hatching in both plots indicates where the models agree in sign. So in the precipitation, you see too much in the southern hemispheres and not enough in the northern hemisphere. So this is the double ITCZ problem. And you see there's also a land component to this, that there's too much rain over Africa and not enough over South America. Kind of interestingly, the Indian Ocean doesn't have these SST biases, but it still has a precipitation bias that would indicate that the precipitation bias in the Indian Ocean is not related to the local SST distribution there. The working group, because of the lack of SST biases in the Indian Ocean, just focused on the Atlantic and the Pacific. And also an interesting thing in this top plot that will be highlighted again further is that the largest SST biases actually occur in the Atlantic off of the equator there. So most of the presentation here is based on a white paper that's currently being finalized. And the main contributors to this white paper are listed below, and these are almost entirely people that have been active in the working group as well. So the history of this working group, it was established in 2012, so we're really just finalizing our activities now with this white paper. It came out of a workshop that was held in March 2011 on tropical Atlantic SST biases that recommended a continuing working group. And at the same time, there were hypotheses emerging on the importance of oceanic eddies to the SST cooling in the Southeast Pacific that would benefit from further address. So the objectives were to promote collaboration between observationalists, modelers, atmospheric and ocean scientists that were active in the two basins, coordinate a model assessment of the surface flux errors for the Atlantic, similar to what had been done in the Pacific by Simon Dezoke and colleagues, identify recent model improvements and common persistent model errors in both CMIP-5 and high-resolution models, and provide recommendations for how to address the eddy oceanic cooling contribution. So we've had telecons. We had a session in fall 2012 with a meeting appended to it, Google site and US CLIVAR website for collecting materials. And then last spring, we had a smaller meeting in Miami where we laid out the outline for the white paper and have been diligently working on that to get that done, and including a smaller meeting this past spring. So we'd really like to get that finished this summer. So I thought I would show the summary just because there's a lot of material in this white paper, and I want to make sure that people see the basic points in their completion before the and then draw your attention to the supporting figures. So just to go through these quickly, we'll touch on all of them again. The most pronounced SST model biases occur in the southeast Atlantic, with the connection to the equatorial biases not yet well characterized. The processes for the cooler SSTs appear to differ between the Pacific and the Atlantic, with ocean processes hypothesized to be more important for the Atlantic. Remote bias experiments suggest that the Atlantic SST biases have a larger global impact than those in the Pacific. Hindcast experimentation suggests that the dominant processes establishing the SST biases vary between the different models. The importance of the ocean eddies to the offshore SST cooling in the Southeast Pacific still lacks a robust consensus. Whereas in the Atlantic, the oceanic processes maintaining the SST distribution reflect a very different bathymetry than in the Pacific, where you have a southwards warm Angola current meeting a cooler northward flowing Benguela current at the frontal region. That's also the site of the largest SST biases. So, and how these coastal features affect the offshore SSTs and the role of the oceanic eddies is has not yet been addressed in the Atlantic, to my knowledge. Both of these basins the two of them have the largest stratocumulus decks on the planet. Their cloud fraction remains underestimated in most CMIP-5 models, and even the seasonal cycle in cloudiness is inadequately captured. The cloud fractions are underestimated even when the SST field is realistically specified, so that implicates the atmospheric model component as the origin for the errors. The gridded surface flux data sets that are used to assess a couple climate models also overestimate the amount of shortwave radiation that's entering the ocean. It's not by much, 10 watts per square meter, but that means that the biases are actually slightly worse than would be suggested by the surface flux products. Improvement in the atmospheric spatial resolution improves the depiction of the coastal winds by improving the model topography. So for this reason, causes for the coastal and the offshore SST and cloud cover biases may differ. There's currently field work has been successful in Southeast Pacific at elucidating causes for SST and cloud errors, continuing in the climate process team studies. This hasn't yet been done for the Atlantic. In the Atlantic, there's ongoing field work right now by the European community that's focusing on the oceanic processes, and there will be upcoming U.S.-funded efforts to examine the impact of the biomass burning aerosols that emanate off of continental Africa and the low cloud response to this, to the shortwave absorbing aerosols. So to dive into the supporting figures for these summary findings, this figure shows that the CMIP-5 model mean biases have not improved much relative to CMIP-3. So in the left-hand plot there, the black line shows the observed SST across the equatorial Atlantic. So you see that it's warmer to the east and warmer to the west and cooler to the east, and that in the model means the gradient is opposite in sign to that observed. There is some hope, though. I mean, some of the individual models do a better job. In particular, this MRI model, the dashed blue line here, is actually doing a pretty good job of capturing the observed SST changes. And this plot on the right here shows the insubstantial improvement between the two CMET enterprises, and also highlights this region of, that's just stubbornly resistant to improvement here in the Southeast Atlantic. So this next figure here just more clearly elucidates the pattern of the biases in the Pacific and the Atlantic, and in particular this region and the Atlantic, as I mentioned before. So this next figure breaks down the individual components of the surface energies biases measured relative to the OA flux product. So the plot on the left is for the Pacific, that on the right for the Atlantic. And what you see is that the shortwave surface energy budget errors really dominate in the Pacific, whereas in the Atlantic these are not so pronounced, and actually the turbulent the errors in the turbulent fluxes are more significant. And actually, it appeared to overcompensate in the Atlantic for the shortwave errors. So this was perhaps for us the initial suggestion that the sources for the errors might differ between the two basins. This is just to orient you to the cloud climatology and SST climatology for the two basins. The lower plot shows the annual cycle in the SST, cloud fraction, liquid water path, lower tropospheric stability, and aerosol optical depth for the Atlantic and Pacific regions over the main stratocumulus regions. So these are, as defined by Klein and Hartman, 1993. So these are, I don't have them indicated on the plots, but they are kind of centered on where you see the highest cloud fraction occurring. So these colored contours of SST distribution, and you see that in the Pacific, the clouds tend to hug the coast more and are more seamlessly joined to clouds in the equator, whereas in the Atlantic, the deck is bounded by the warmer SSTs to the north. I also have the coastal jets indicated on these figures. They're both much stronger in the southern hemisphere than they are in the northern hemisphere. So the shortwave cloud radiative effect from, so the most important thing of these clouds for the SST distribution is their radiative effect at the surface. And the top plot shows the CMET5 model mean over 1950 and 1999. The bottom plot shows the bias relative to Theory's EBAF product, and again highlights the how high these biases are in the Pacific relative to the Atlantic. This shows the seasonal cycle and the cloud fraction for the two basins at the top, and in the liquid water path at the bottom. The more pronounced solid lines are observations, and the gray lines are the individual models. And most of these models have a seasonal cycle that's not in phase with what's observed. And there's a couple of models that do a bit better, and nicely for the U.S., the CCSM4 and the CESM CAM5 models do a bit better at capturing the seasonal cycle accurately. So this would tell us that either the clouds are not responding to large-scale conditions correctly, or the internal representation of the clouds is not accurate. And we tend to think that the issue is more with the internal representation of the clouds. For example, through plots like this. That this is just for the CESM CAM5 model with respect to observed satellite-derived low cloud fraction. So the observation is shown in the top panel. The coupled bias is shown in the middle. And when a comparison is done to a AMIP simulation with realistic SSTs, you see that the clouds the cloud bias is not that much improved. So let's see, I think I'm going to skip over this next slide so I don't end up dominating the discussion with the clouds, since we only have 10 more minutes left. But I did want to point out that when both regions are forced with a realistic atmosphere in an OMIP simulation, that the SST biases also appear. So the SST biases must also have an oceanic contribution. And this is based on a paper from Gökhan Danabasoglu that came out last year. The oceanography is very different between the two basins. So I mentioned this earlier, but this plot by Ming-Kui Li nicely highlights where the Angola-Benguela front occurs at about 16th south. So this is where the largest SST biases occur. So there's been some attention paid to that region. Ping Chang, Justin Small have, and their research groups have been focusing on this region. And one issue appears to be, so this is a plot of the surface wind stress curl from CMIP 5 on the right here and core 2 on the left. So you see that the wind stress curl is more pronounced in the CMIP 5 models than in the core 2. So this is related to in the atmospheric resolution, that you have the coastal winds are underrepresented in the CMIP 5 models. So then you get too strong of a gradient between the coastal and offshore winds, leading to a too strong of a surface wind stress curl. So this might kind of, so this would encourage upwelling, which you would think would be good for the SST biases in that region. But because of this, the complicated, I'll go back to this plot of the currents, because the dynamics of the Angola current meeting the Benguela current at this region are quite complex. Work that Ping Chang has done and Justin Small indicates that either the Angola current continues too far south, or that the upwelling is encouraged, but it's of this warmer Angolan waters that still contributes to these warm SST biases in this region. I hope I represented that work correctly. My background's not in oceanography. We've looked at the impact of resolution changes. So the plots on the left are from modeling efforts done by Ben Kurtman, and on the right by Justin Small. And the top plots are done at 1 degree ocean atmosphere resolution. Bottom plots are at a higher resolution, 0.1 degree in the ocean and half a degree or a quarter of a degree in the atmosphere. This warm bias in the mean in here is related to a sea ice melting event. And so the thing to focus on in here is that while the west basin boundary currents, their depiction is improved as you go to higher resolution. In both of these, you also see some improvement in the CSSM in the southern hemisphere Atlantic. There's still that region of very stubborn, persistent bias, and in the CCSM4 resolution changes, you don't see an improvement in this region at all. We've looked at at assessing these surface flux gridded products. I should have maybe put this slide earlier in this presentation. The main thing we learned from that is that these are the buoy values of the Stratus buoy, for which we have a 9-year time series that overlaps with theories, OA flux, and era interim. At the Parada buoy, we only have 1 year. That relative to the buoys, the other data sets are putting too much shortwave radiation into the ocean. So how do we attribute the SST bias? There's been some interesting work looking at fast versus slow SST error growth work. The Tomiazzo and Wolno paper, they looked at 3 models in the CMEP3 archive that had enough data to be able to assess error growth that occurred relatively quickly compared to the slower growth. And this is encouraging further work in this area. These plots were made by Ben Kurtman. The top plot shows the error over the first 5 days in a 10-member CCSM4 ensemble, and the bottom plot shows the error after about a year has passed. And the structures are very different, but nevertheless you already see sort of the seeds for the warming in this region down here appear within the first week. So this is we view this as a maybe a hopeful avenue for future work, in that these fast SST error growth processes are easier to diagnose than after time has set up to establish the larger feedbacks with more remote parts of the atmosphere. So so we suggest this as an avenue for further exploration. We've looked at the impact of the Atlantic and Pacific biases to the global climate, because after all, we're justifying the effort to look at these biases by their importance to the global climate. So these are for 3 models, the CAM 3, 4, and 5, and the top 6 plots are for the Atlantic and the bottom for the Pacific. I know these are a little hard to read. The way that these were done was by setting the Q fluxes, the internal oceanic heat transports, to 0 in the indicated boxes, and then seeing how the model evolved to those. And the main point that we drew from these plots are when that the SST biases in the Atlantic find a a remote impact in the Pacific, where you start to see this double ITCZ. Well, this is in the SST. This is in the precipitation, and this is the SST. But you start to see the double ITCZ establish itself. Whereas when this experiment was specified in the Pacific, we actually did not see a response in the Atlantic. I see that our time is really near the end, and I'm not leaving much time for comments and questions. This is the summary again. I wanted to note at the end, well, here's one slide indicating the field work that's happening in the Atlantic. So there's a large EU-funded PREFACE project that some of the ETOS working group members are also involved with, Peter Brandt, Robert Machoso, Ping Chang, that's looking at understanding the SST biases better from an oceanographic point of view. It also has a large modeling component, and also involves a lot of African scientists. And then from the American side, there is field work that's happening, that's coming up in the next few years, that's going to be focusing on the smoke that emanates off of the continental fires and is advected westward over the remote Atlantic and the low cloud response. So far these activities are not yet connected, but certainly as the data sets come out of both, I think there will be opportunity to benefit from each other's efforts. So I'll end here, and I apologize. I went a little longer than I should have, I think. But these are the recommendations that we have come up with so far. So encouragement for the individual modeling centers to identify and improve the sources for their models' biases. Further development of the high-resolution coupled models with a concurrent emphasis on parameterization development for the small-scale processes that even the high-resolution coupled models will have trouble capturing. And the focus on the climatically influential eastern basin coastal oceanic upwelling regions, including perhaps through a coupled climate process team that includes both oceanographers and atmospheric scientists. So the CPTs to date have been either atmosphere only or ocean only, but the coastal jet region and upwelling region, it's such a coupled process that this would be a valuable area in which to involve both expertise. Further model improvement that will incorporate data from these recent and upcoming field campaigns. And lastly, fuller, try to make better use of the buoy data sets that are out there and towards improving the gridded surface flux data sets. Although the Atlantic, it has a lot of buoy data there, but actually when we looked into these for doing an assessment of the gridded data sets, we found that most of these are not full flux data sets, and also the data sets are very intermittent and difficult to use in a climate model validation capacity. So I'll end it here on the slide with the recommendations. And I wonder if there's any comments or maybe other input from the other members of the working group that are on this call. Also, if there's any further questions, do feel free to email me.
Yeah, we could stay on for some time in questions, and we have a few people who have raised their hand. Paquita, not sure if you saw, but your co-chair, Simon, left us a comment, kind of a clarifying comment back when we were talking about the upwelling and the wind stress curl, and I'll read that for everyone. He said the upwelling comes from deeper when it is trapped close to the shore. Distributed wind stress curl away from the coast will upwell water, but from less deep in the ocean, hence probably not as cold.
Oh, thanks for that.
Great. Okay. Let me unmute. Carlos, but I think, is this Alberto?
Roberto?
Yes, hi, Alberto. We can hear you, so go ahead and chat with Paquita if you have questions or comments.
Paquita, one comment on something that you said that was very reasonable, but I think that can be qualified a little bit. You talked about the experiments with perfect SSTs, and you were saying that because these experiments still have errors, this highlights the internal processes, and this is a very reasonable hypothesis. I believe also that we are not quite sure even if they run with perfect SSTs have a good enough large-scale field simulation to have the right stratocumulus clouds in the tropics, because we still do not really know the fundamental question of what has to be achieved with the stratocumulus simulation. And since maybe very, very delicate point, and it may not be clear that maybe small changes in the downwelling over the stratocumulus regions may have a very large effect on that region, as well as the changes in the upwelling in the ocean can have SST changes that are very important. So there are feedbacks. So I think that we do not really know if the uncoupled models are doing a really enough good job, a job that is good enough in the stratocumulus region.
Meaning we don't quite know what we haven't quantified how important the cloud errors are relative to SST, the oceanic processes.
Well, I think that you said what happens if you put the perfect SST? So cold simulation is better, but we do not know if it is better enough to solve the problem of the stratus. That's my point. And the reason that we do not know is that we do not really exactly know at this moment what is the relationship between the stratocumulus and SST that determine the coupled system in the eastern part. So it requires more fundamental work. No question that there is no question that people have improved parameterizations of PBL and results are better, resolution is better, and has improved. But the ultimate reason I believe we do not really know.
Right.
Great. Anything else regarding that, or do we want to go on to Rob Wood, who also has his hand raised? Rob, if you want to go ahead, you're off of mute.
Okay. Yeah, thanks, Paquita. I was wondering if there were any developments in terms of measurements in the ocean, cruise kind of measurements planned for the next few years over the Southeast Atlantic that you can speak to.
Yeah, I see that Peter Brandt is on the call, and he is very involved with this PREFACE project, and also the PI of something called SACUS, Southeast Atlantic Coastal Upwelling Study. So this slide at the end, I'll try to get there again, was these measurements that are being taken here, the glider measurements, and the SACUS experiment started in 2014, I think, and PREFACE is underway right now. And I don't know what the status is of that. If Peter wants to speak to it, that would be useful. I do know that there's a big PREFACE meeting happening in Cape Town, South Africa in late August. Roberto is going to that, Ping Chang. So that would be useful.
Okay, thanks.
Well, I think Peter may be trying to
Yeah, Peter, you're off mute. If you want to try speaking up.
Do you hear me?
We can hear you. Yes, you're a little quiet, but we can hear you.
Okay. Just to say a few words to the PREFACE experiment and the SACRIS experiment. One of the main aim is the measurement of the eastern boundary circulation, and there at the moment are 3 moorings in place, so that it's 18 degrees south, 20 degrees south, and 23 degrees south. But those moorings are really at the shelf. It's really in shallow water, maybe 100-meter water depth or something like this. The mooring at 11 south, so measuring the strength of the Angola current and the transport water southward, is in the water since 2013, and the next cruise will be in October this year, with these glider transect that you see here in the black line, so that the different glider transect we plan for this year cruise, and the next cruise is scheduled for next year also, something like September, October 2016. It's a similar schedule, replacing the moorings and at the glider experiment to measure also the exchanges at the Angola Benguela front at about 17 sounds.
Great, thank you. Alessandra, you are off mute. You may have a question or comment.
Hi, yes, can you hear?
Yes, we can hear you.
Hi, Kristen. Paquita, thank you for the presentation. I just wanted to make a note and kind of follow on to what Roberto was saying. I found it very interesting what you mentioned about the NCAR models, SESM and CSM doing somewhat better in the simulation of the seasonal cycle of cloud cover, if I understood right. The note I wanted to make is that it's interesting that in those models, the representation of convection has also changed quite significantly, and so I'm just wondering what the connection there may be. And what I know, something that I looked at specifically is that relationships of West African monsoon precipitation to SSTs have also changed quite significantly and are more as in the observation, in the coupled simulation. So I just wanted to make that connection for us to maybe something to look into. Thank you.
Okay. Yeah, I've interpreted this plot to indicate that the clouds are a bit too bottom up. You know, that they're not doing a good job at capturing the cloud top inversion and the top down driving of the stratocumulus. And to my mind, that would explain why you're not getting the right seasonal cycle. But yeah, that connection to the West African monsoon, that's a really good point. That's interesting.
Thank you.
And Paquita, do you want to pull up the CSM1 and CAM5 Medeiros plot? Simon had another comment about this one.
This one?
Yes, I think. Yeah. And he noted, I don't know if you can see the chat box, but Simon noted that the low cloud fraction errors are on the western side of the stratocumulus cloud deck, where stratocumulus are transitioning to trade cumulus.
That's right, yeah. So this would suggest that the stratocumulus is transitioning too quickly into trade wind cumulus. So it's becoming bottom up driven too quickly. And that makes sense given the coarse atmospheric vertical resolution compared to what you need to capture the stratus correctly. It's a really hard problem. I don't actually know how to get around that.
Great. Do we have any other questions or comments for Paquita or any of the others who are on the line? Good. I don't see anything. Oh, wait, Peter has his hand up. 1 second.
Hi, Patrick Thomas Soniato. I'm sitting here with Peter Brandt, listening in. Hello, everyone. Yes, I just wanted to I wanted to make the point Roberto made very, very usefully. So that's one. I think that we need to pay attention to the circulation when discussing cloud biases, because a lot of those can be associated with circulation problems, and we know for sure that we have very large circulation problems in the South Atlantic from many CMIP-5 models, and CAM in particular is a very clear example of that. So in CAM there are deficient cloud from the start, and it's one of the models that have large cloud deficiencies. However, there are models that are not that bad, and I would be cautious to generalize the cloud problem that do occur in a few of these models. CAM in particular is hampered by a poor boundary layer parameterization and a virtually non-existent inversion in the stratocumulus areas. To other models that maybe are doing a better job. From the analysis, I think if you want to attribute causality, it is not recommended to look at simulations that have reached their climatology, because there everything will be in balance. And it is when looking at forecasts, as Paquita has shown, that we gain some insight of which errors are generated by which processes due to the fact that they are split spatially and temporally, and that allows to make this distinction. In the analysis of the CMIP-5 models I've done so far, and that we are doing now for PREFACE on the forecast from the CMWF, seasonal forecasting system, that's an example, and in the ECR decadal forecast, so the decadal forecast made with the ACF model, which is NEMO plus open IFS. We see that the atmosphere is producing very rapidly wind errors, and these wind errors do not seem to be sensitive to coupling at all. This is one type of error we see, and the other one that I've found in all the models I've analyzed so far is that when they're quelling, at least the wind-driven part of their quelling in the Benguela region should pick up around Boreal Spring, it actually doesn't. That means that cold advection in the ocean is insufficient, and that leads to a warming, and that warming then comes back, both the wind and the atmospheric profiles. It involves the clouds in the end. And some of these errors is locally wind-driven, some of that is actually originating from the equator. And that seems to be, so far, it seems models all have this type of problem. I really like Justin Small's spacing paper, which is probably about, it's in revision for climate dynamics, but should be accepted soon, I expect. Where he shows that the current structure of the Benguela and the associated cold advection, therefore, is actually very sensitive to that wind distribution. And that while coastal upwelling itself can drive, in fact, cold SST errors in regional ocean models that have the right hydrography because it's dictated by the boundary conditions. In global coupled models, the advection implied by relatively small wind errors can lead fairly quickly to large SST problems. And that is associated both with the wind driving, but also with the subsurface hydrography. So I think we have to be a bit cautious not to put too much emphasis on one thing rather than another, because the contribution from surface fluxes and from dynamical forcing of the atmosphere, so far as we've seen so far, are equally important, and similarly, the contributions from local forcing and from remote connections to the equator are also equally important. In recent experiments we've done with CAM, we see, for instance, that the wind thrust bias over the equator in the Atlantic is driven about half by local SST biases, and the rest comes from the Pacific. So it's not a local wind error either. So we are looking at a very complex problem, and I just would like to stress the fact that a narrative in the paper is great, and we need it in order to obtain some conclusions, but it's also important to stress the fact that we don't, at the current time, understand what the ultimate causes of the errors are. And that, so far as we know, local, remote, atmospheric, and marine errors are all contributing. Thank you.
Okay. Thanks. Are there any more comments?
Any other questions or comments? I don't see anyone. Apologies, Rob had a little bit of difficulty here at the end. He lost his sound, so I may have to troubleshoot with him to see what happened, but I think everyone else was still able to hear. So let's go ahead and wrap it up. Thank you very much, Paquita, for presenting today, and everyone for joining us online for the webinar. If you can join us next Tuesday, the 23rd, we'll have the third and part of our series where we're hearing from the Arctic and Mid-Latitude Working Group. I have a recording of this presentation as well as a PDF of Paquita's slides that I will share with the group as well as post on the website. So you'll have those in about a day. Thank you and have a nice afternoon.
Okay, so you'll email us where the presentation is?
Yes.
Okay, great.
And I can share your email with the group as well, so if anyone has further questions, they can follow up with you individually.
Okay, great. Well, thank you all very much.
The conference has been unmuted.
Great. Thanks, everyone. Have a good day.
Thank you. Bye-bye.
Bye.
Bye.
Bye.